All right, let's move on to the second talk, which is by Tianyu Chen, Kevin, as he calls himself, who is a third-year PhD student in computer science at the University of Massachusetts Amherst. So I guess Massachusetts is well represented in this session. Now, Kevin seems to be very passionate about video, and he does all kinds of algorithm design for all kinds of video, adaptive, 2D, 360-degree, volumetric, and immersive. So over to you, Kevin, to talk to us about video streaming.
Nice. Thank you for the introduction. Hi, everyone. I'm Kevin Chen. Today, I'm proud to present our work, SODA, an adaptive bitrate controller for consistent, high-quality video streaming. This work is a result of the collaboration between University of Massachusetts, Amherst, Caltech, and Amazon Prime Video. Before I start my talk, let me do a brief survey. Could you please all raise your hand if you watch online videos through some kind of platforms like YouTube or others? Okay, very nice. So I think I don't need much motivation for how important video streaming plays in the role of our daily life. But I still want to give you a brief introduction of how adaptive bitrate streaming, the main algorithm behind video streaming, works. To prepare content for adaptive bitrate streaming, we first segmented a video into smaller segments, say 2 seconds each, and then we encode the video stream at different quality levels so that the client can dynamically adjust the quality level according to the varying network connections. Let's consider a concrete runtime example. The ABR controller may start by downloading the lowest qualities. The downloaded segments are placed in the buffer until they are ready for playback. As the network condition gets better and better, the ABR controller may become more and more aggressive and start to download higher and higher qualities. Of course, things are not always so rosy. At some point, the network may deteriorate, and the next segment, unfortunately, fails to arrive before the buffer is completely drained. In this case, the client encounters what we call a rebuffering event. Think about the time when you're watching your favorite TV show and the loading screen pop-ups. That is super annoying, right? After this, the controller may back up and start downloading lower qualities again. I hope from this simple example, you get some initial sense of what are the major goals that an ABR controller is striving for. To be more concrete, there are 3 major quality of experience components. First of all, obviously the user wants to watch their videos at the highest possible qualities. However, they don't want to do so at the expense of experiencing rebuffering events, which is very annoying. The third point is a bit subtle. Although ABR works by switching bitrate in accordance to varying network connections, doing this too much can actually hurt the user experience by itself. The reason is that fluctuating bitrate will result in a very inconsistent video viewing experience. In fact, from the production data at Amazon Prime Video, we noticed that when the bitrate switching rate is more than 20%, the user is likely to abandon a video stream even before watching 10% of it, a very negative user experience. Now, ABR has been quite studied extensively in the literature before. There are 3 major groups of design. Super-based controllers just select the bitrate according to the current predicted network super, very straightforward. The second group, buffer-based controllers like Bowler and BBA, look at the current buffer level and select a bitrate decision. They tend to be more robust, but unfortunately, they also tend to switch bitrates more often. The third group, hybrid, where most design lies in, try to take into account both the predicted super and the current buffer level when making a decision. Now, those of you who are familiar with the ABR literature may wonder, there are so many existing designs, why do we need yet another ABR controller? And why do we need SODA in particular? I would like to argue that despite numerous studies in the literature before, there are several desired properties that we want for an ABR controllers that are not simultaneously met by any of the existing designs. More specifically, video providers want to provide consistent and high-quality viewing experience to all users, regardless of what devices they are using, what network connections they are on. By consistent, I mean lower rebuffering and low bitrate switching. Second, we want to do so with theoretical guarantees for all three QoE components. We don't want just a heuristic solution that may or may not work. We want solid theoretical guarantees. Third, we want our ABR controller to be robust against throughput prediction errors, which are inevitable given the in-the-wild network diversity. And finally, we want our controller to be practical for production deployment so that we can actually realize its impact on end users. Now is the time to give you a very high-level overview of what is the structure of SODA. Given the predicted throughput, SODA tries to minimize over the next k time intervals. Notice I say time intervals, not video segments. More on this later. It tries to minimize over the next k time intervals the sum of distortion cost, buffer cost, and switching cost, subject to buffer dynamics and constraints. The three cost components correspond to the three QoE factors responsively. Now, at this point, it all seems pretty abstract. The key question is, how should we design each of the three cost functions, and how should we design the buffer dynamics to give us theoretical guarantees and robustness guarantees? To do that, we leverage insights from smoothness optimized convex optimization from the theory community. So smoothness optimized convex optimization, in short SOCO, is basically online convex optimization with switching costs. So we need to somehow transform the complex ABR problem to an instance of the SOCO problem so that we can leverage the rich literature from the theory community. The transformation turned out to be highly technical and challenging. In fact, it is impossible for all the traditional formulation. I will not bore you with all the mathematical details here. I'm sure you will all fall asleep if I do so. Instead, I would like to give you two main key modeling insights that we make that enables us to do this transformation. And these two key modeling insights are what I hope you can take away from my talk. The first modeling innovation we make is to pivot from a segment-based view of ABR streaming to time-based view. Traditionally, because video streaming works segment by segment, people always try to plan for the next several video segments and try to optimize for this segment sequence. This is more like a discrete problem. Instead, we think about video stream as a continuous fluid stream. You make decisions in a continuous fashion. More specifically, we make decisions for the next first seconds, next second seconds, and so on. In this case, the problem becomes smooth and more tractable for theoretical analysis. It also gives us some additional benefits, like avoiding the pitfalls of causal loop, which you can refer to in our paper. The second modeling innovation we make is we transition from modeling rebuffering time directly to modeling buffer stability. The function you're looking at right now is how people traditionally do this. Traditionally, people only impose a penalty on their ABR formulation when there's a rebuffering, when there's an expected rebuffering. However, that's like only reacting when there's a packet loss, which is already too late. Instead, we choose to model buffer stability. More specifically, we try to steer the buffer level towards a target buffer level and impose an increasingly large penalty as the buffer level dips below the target. In this way, we can show that SODA behaves much more robust in practice. Now, what do I exactly mean by SODA is robust? Through theoretical analysis, we can describe a very nice property about SODA called exponentially decaying perturbation property. Let me walk you through this through an illustration. Let's say the black line here is the optimal trajectory of an ABR controller. Each state in the diagram represents buffer level and bitrate chosen. In practice, no ABR controllers will conform to this optimal trajectory. There will inevitably be mistakes. But what we can say about the mistakes made by SODA is that the impact of every mistake made by SODA will decay exponentially fast into the future. In other words, this means that SODA's mistake do not have a cumulative effect in the future. So one mistake will not make it regret forever. As you can see, even at each time step in practice, Soda may make a mistake, but it can quickly recover from it and will not be too far away from the optimal solution. What this property shows is Soda will be highly robust in practice, and to be more mathematically precise, we have a theorem that states that the total cost incurred by Soda compared to that of the offline optimal is only 1 plus big O rho to the k, where rho is a factor smaller than 1, and k is your look-ahead window length. Notice that a ratio of 1 essentially means your controller is optimal. In our case, since there's only an additive exponentially decaying factor, what it means is that as the look-ahead window increase, our Soda's performance will converge to the offline optimal exponentially fast. Now, it's not just good to have theoretical guarantees, we also want to show that Soda actually performs well in practice. We conduct emulation experiments on Puffer, which is an open source ABR research platform. We compare Soda against a wide range of baselines. The takeaway from our empirical evaluation is that Soda achieves the highest mean quality of experience by a significant margin against state-of-the-art baselines. And to do so, it achieves a reasonable quality, but more importantly, significantly lower rebuffering ratio, meaning it's highly robust, and also the lowest bitrate switching, meaning it delivers a highly consistent video viewing experience. Inspired by the great emulation performance, we decide why not give Soda a try in an actual production deployment. But to make that happen, we have to guarantee that Soda is practical for deployment. By practical, I mean it has to be very efficient in terms of runtime complexity. Now, what prevents many of the existing research design from going to deployment is that many of them has to solve an optimization problem in a lookout window, and Soda is no exception. We have to consider all combinations of the bitrate in the short-term future and find out which one is the best. If you think about it, there are exponential amount of combinations. Doing this naively using brute force or using a commercial server is obviously a no-go in practice. Some researchers propose a table lookup, but that's not scalable, and also it will incur high operation overhead. What we find that, our insight is that in practice, what most people are doing is predicting having a constant point prediction. And in that case, through our theoretical analysis, we show that Soda we only need to consider monotonic bitrate sequence when solving the optimization problem. By monotonic, this is not a monotonic sequence, but this and steadily increasing, or you can also have steadily decreasing sequence that are monotonic sequences. So we only need to consider all the monotonic sequence, and that translates to only like less than 150 iterations in practice, which is not a big deal even for low-end devices. Now, we have made sure Soda is highly efficient, and it's time to give it a try in production. Thanks to colleagues at Amazon Prime Video, we are able to deploy Soda in more than 10 countries across a large user base, where we conduct large-scale double-blind randomized control trial on a large range of users and devices families. What I want you to focus on first is how much Soda reduces the mean bitrate switching. In fact, Soda reduces mean bitrate switching by almost 80% compared to a well-tuned production baseline. This is not a typical performance improvement we'll see in a production system. Think about it, 80%. This is a huge implication for the end user experience. What's more amazing is that in achieving so, Soda does not sacrifice the other key metrics like mean bitrate and the rebuffering ratio. In fact, it even reduces the mean rebuffering ratios. Another takeaway I want you to have from our production deployment is that it demonstrates that Soda is indeed highly practical. It's not just a research toy, it is efficient enough to even run on low-end devices like set-top boxes, which has very limited CPU and memory resources. Another takeaway I want you to remember is that in doing so, we do not involve any sophisticated super predictors like some prior works do. We only use a simple sliding window predictor, and that's enough to guarantee that SOBA has high performance and robustness. To summarize, with time-based and buffer stability modeling innovation, we can successfully transform the ABR problem to a SOCO problem and leverage the insights from the theory community to provide theoretical insights for SODA and robustness guarantees. Through numerous empirical evaluations and production deployment, we show that SODA is highly performant, robust, and practical. Finally, even if you do not work in video streaming directly, I believe the theoretical insight behind SODA can be potentially transferred to other networking domains as well. In particular, the exponentially decaying perturbation bound that I just described is a property that I believe many other network systems should strive for as well. That concludes my presentation. Thank you very much for listening.
Very well kept your time, so we have ample time for questions.
Really cool work. I'm Amar from UIUC. My question is, so you say that the bitrate switches, they have like significant effect on quality of experience.
Yes.
Do you have like some, as in like data to kind of show that, like from production or something? As in a sense that the video sessions which have higher changes will also tend to have lower quality of lower bitrate and everything as well, right?
Yeah.
How do you kind of isolate the effect of two?
Yes. Could you bring the presentation slides up again? Okay. In the QoE experience, in the QoE figure, I showed some data about when the bitrate switching is larger than 20%, the abandon rate is like before watching 10% of the stream. We have a figure in our paper. That data is collected from, here it is. Here's the data. I didn't include the figure here, but you can refer to the detailed data in the paper. I want to comment that in this data, we exclude the rebuffering effect by only consider streams which do not experience any rebuffering and are all streaming at a decently high quality, so the only difference is switching effect. But I do want to caution that this is a correlational observation, so there might be more complex reasons, but I think it's a decent indicator of it.
Okay, thank you.
Yeah, thank you for your talk. This is Tingting Yuan from University of Göttingen, Germany. My question is about why you don't compare with the RL-based algorithm like the Pensive in your simulation.
Yeah, thanks for the question. We actually do compare with RL-based algorithm. Let me go to the empirical evaluation figure. Yeah, here you see that we have the last baseline is causal same RL. That is the re-implementation of Pansy by the causal same monitors using their latest causal same infrastructure. So that is indeed a modern implementation of reinforcement learning-based ABR algorithm.
And then the comparison is fairness because the QE maybe varies because the function.
Yes. That's why we not only show QoE in our paper, but we actually show the individual components. So you're free to examine the individual QoE components and compare our algorithm SODA with each of the baseline based on the individual components.
And the QE, there's three factors, right? So there's weights about the three factors. So I question about maybe only the last one has lower performance. Maybe the rate is so low, so when you're training the reinforcement learning, it's not tend to a lower switch rate.
Yeah, that is actually an issue with reinforcement learning algorithm. In practice, you do want to try with different kind of weights, but it's not quite operationally feasible to retrain your reinforcement learning model every time you want to try a different combination of weights. That will incur a huge operational overhead. And that's what prevents reinforcement learning algorithm from being adopted in the industry.
Yeah, okay, thank you.
Thank you.
Iman Ramadan from University of Minnesota. Nice work and talk, of course. So I was curious about when you changed the discrete decision-making for the ABR at the chunk level, which we are familiar with. That's when you actually change the quality for the next chunk. So you mentioned that you actually changed that to continuous time. So can you please elaborate on that? And when do you make the decision about the next chunk or next quality? Look, how these interleave?
Yeah, let me clarify on this. So the continuous formulation is is for two purposes. One is for theoretical analysis, and second is for the optimization phase. In practice, because video arrives segment by segment, we do have to commit the decision to each segment. So I do admit that the model is not completely the same as what it is in practice. But as an old saying goes, like all models are wrong, but some models are useful. I believe our models are indeed useful.
Okay, thank you.
Hey, nice work, Kevin. Vyas, author of MPC, thanks for beating it. So, quick question. So I'm curious, like, how sensitive is this scheme to the number of bitrate levels available? Because I can imagine, like, if you're a sort of a provider, depending on different devices, may actually have like various levels of discreteness in how much the bitrate jumps. Like, there's also like a CDN cost with keeping like different manifests and so on. So did you do any kind of sensitivity? Because in the limit, I have like almost like continuous bitrate levels, and the other extreme, I have like super discrete ones.
Yeah, that's why we actually don't pre-encode everything. So every decision is made on the fly. And to make that fast, we first, as I mentioned, we adopt a monotonic strategy to only consider monotonic sequence. And in case your bitrate ladder is really, really large, like you have like 20s or 30s bitrate, the observation is that you don't really want to jump bitrate at any chunk at any segment. You don't want to suddenly jump from 1 to 30 the 30th bitrate. So you can limit the range of the bitrate you're in consideration during the optimization, and that will greatly reduce the runtime complexity.
Cool, thanks.
Yeah.
I'm wondering if this mic works. I might ask a question as well, since I have you here. Your randomization when you did this field trial, I'm just clarifying, was it truly randomized? There was no bias in terms of region or kind of player or type of content. It was truly randomized on a per session basis, whether or not to use your algorithm. Is that correct?
Unfortunately, I can't give more. So I can't say exactly how the system works because of legal issues, obviously. Okay. But I can say like it's for each so for each region you can like randomly select just for instance 0.1% use algorithm A and 0.1% use algorithm B, and this is completely randomly assigned.
Okay, well done, fantastic. Let's thank the speaker again. All right, I think we can move to the next talk.